Hey guys, welcome back. Today we're going to be talking about igneous rocks. We've been kind of doing the trek through minerals. We start off with atoms and minerals. We've been through plate tectonics and the rock cycle. We're going to start with that first part of that rock cycle, igneous rocks. Igneous rocks are extremely cool. They're kind of the easiest place to start studying the rock cycle from. Of course, we can start at any of the locations. Some people have even said that metamorphic rocks might be the better way to go. I actually think igneous rocks are the best way. Most textbooks start there, so that's where we're going to do it as well. So what is an igneous rock? Well, you can kind of get the idea if you know a little bit of Latin. Igni in Latin means fire. So this is means igneous means fire-born or fiery rocks. So igneous rocks form as molten rock cools and crystallizes. So it'll form crystals, and of course we know that crystals are important because crystals are the fundamental units of minerals, right? So we're actually generating minerals in igneous rocks. Okay, so you don't want to fall into the trap of saying that, you know, that when the rock cools off it freezes or it hardens or any of those other things. Those are after effects of the fact that it's crystallizing. We'll get into why it crystallizes a little bit later. So there's some general characteristics that we want to talk about. First off, that the parent material of igneous rocks is very important for determining what kind of rock comes out of it. In other words, if you melt a sandstone, you get a very different kind of igneous rock than if you melt a basalt. And that it forms from partial melting of rocks inside Earth. So generally speaking, we don't see that the melt or the molten part of magmas, the origin of these fire-formed rocks, comes from melting entire rocks. It turns out that most rocks are just partially melted, that there's a solid part that remains behind and a liquid part that moves off and forms the magma that comes to the surface. And that magma that reaches the surface is called lava. And so what do these two rocks here have in common? Well, this, of course, is I believe this is the Pu'u'o'o vent here on the Big Island of Hawaii. And this is a piece of granite. And they are both, in fact, igneous rocks. They were both formed from the formation of molten lava, or molten magma, actually, molten rock, that emplaced itself either up onto the surface of the Earth in the form of a lava flow, like what we see down here, or it didn't make it all the way to the surface. It actually formed a blister, and when it forms these blisters, it actually forms nice crystalline rocks that we can see the crystals very easily. As a matter of fact, here we can see some K-spar, some albite, and there's some quartz and small amounts of biotite and hornblende in here as well, probably mostly biotite. Okay, typical granite, and then of course we see here mounds of typical basalt. We're going to talk about what makes them different. You know, they both come from the same source, molten rock, but why are they different? Okay, so to really have a good idea of igneous rocks and where they come from and what makes them tick, especially when you get into volcanoes, what makes them tick, is you have to understand that what makes a molten rock. Okay, first off, we need to understand that there are three components to magma. There's a liquid portion called melt, a really original name, but we do. In fact, we call it melt. And this is composed of mobile ions. Liquid, it's a liquid ion. Okay. Solids are the second stage, if any. There's not always solids, but if they're present, they're usually silicate minerals that have already crystallized from the melt. Usually these minerals are really high temperature minerals like olivines and hornblendes, things like this that are already present. And then volatiles. And a volatile just means it's a gas that is dissolved in the melt. So just like a soda pop, right? You can dissolve, when you open a soda pop, the bubbles of carbon dioxide come out. The same thing in magmas is that you actually have dissolved gases within the magma that come out when they get towards the surface, if they happen to get close enough to the surface. But the typical volatiles that we see, or gases, are water vapor, which is steam, H2O, carbon dioxide, CO2, and sulfur dioxide. And of course, H2O and CO2 are necessary for life, right? Photosynthesis here, and water is for everything else. Sulfur dioxide is used by some organisms, but to human beings, this is a very toxic substance. So in this picture we have up here, we actually have a vent where down below is going to be some some form of magma. The magma is actually letting off some of its volatiles. In this case, it's probably a combination of water vapor and some carbon dioxide. But I'm sure if you were standing here, you'd smell a rotten egg smell. It would be pretty heavy, and that's a sulfur dioxide. Okay, so probably are seeing, if you were to go down deep enough, you'd find all three. But anyways, this is called a fumarole, and fumaroles are present pretty much in almost all active volcanic systems. It's that gas coming out of the volcano. Even when the volcano is not erupting, the gases are still coming out of the magma, in the magma chamber down deep. Okay, so some other important characteristics we need to understand is how magmas crystallize. What determines how big the crystals get and what they're made out of. So it turns out the way we classify magmas and igneous rocks is based upon these schemes. So the texture in igneous rocks is determined by the size and arrangement of mineral grains. Okay, that makes sense, but here we can see pretty rapidly these are two rocks with very different size of mineral grains, but the main difference between them is just the size, because the composition is identical between these two. So even though this one is gray with white speckles in it, and this one is white with some dark zones in it, this is classified as a different kind of rock than this one. And the reason why is because of the grain size. Chemically, they're identical to one another. So igneous rocks are typically classified by their mineral composition and their texture. So you can have the same mineral composition as these do and get different textures, and that causes them to have different names. This is something called a granodiorite. This is something called a dacite. Okay, some more vocabulary that we need to kind of keep in mind as we're going through. Rocks formed from lava at the surface are classified as extrusive or volcanic rocks. Makes sense, right? Anything where the magma reaches the surface, it's going to form lava, and it extrudes out onto the surface. Extrusive. Okay, that's an important thing to keep in mind as we go forward when we're talking about mineral characteristics. Rocks formed from magma that crystallizes at depth are termed intrusive or plutonic. Pluton from Pluto, the Greek god of the underworld, right? So they're called plutonic rocks. So in this case, this would be the place where you'd have a pluton come into place. So at this point, we've gone over the textures of igneous rocks and mentioned that you can have, in fact, the exact same chemical composition and they be completely different rock classifications. And the reason why we classify them differently is because you can have rocks that don't make it up to the surface, plutonic rocks, and you can have rocks that do make it up to the surface, something that you would call lava. You don't want to make the mistake of calling it a lava rock because there's actual names for these types of things. But when they make it up to the surface, they usually form a different size crystal. So they look very, very, very differently. All right, so first off, we should define, before we go into this chart here, what a rock is. And so all rocks are an agglomeration of two or more minerals. That's actually the definition of a rock. It's two or more minerals put together into a single block or substance. Okay? Most igneous rocks are composed of common rock-forming minerals, right? We went over these in a previous lecture. This is your quartz, your feldspar groups, your biotite, muscovite, you name it, it's all there. And of course, you cannot forget the ferromagnesian silicates, the black minerals that are so important. A lot of people forget to think about those. Quartz is so beautiful, feldspars can be pretty beautiful. But the ferromagnesian silicates are extremely important in determining what the behavior of these rocks are, or I'm sorry, of the magma is within the earth. So when we start looking at the minerals, we realize, well, let's start up here actually. Light-colored rocks that are coarse-grained, remember the ones with the big crystals. In this case, the light-colored one would be a granite. The medium-colored one would be something called a diorite. And a dark rock would be called a gabbro. We'll come into these groups a little bit later, okay? But there's a fine-grained equivalent, an extrusive version, right? And these would be the rhyolite, the andesite, and the basalt. And if you read this way, straight up and down, you'll realize that these are the minerals. In this case, what's in a granite? Feldspar. It's going to have about 75% feldspar if you read it right here in the middle of the chart. And down here, you're going to have about equal amounts of ferromagnesian minerals. This would be like your biotite or your hornblende. And quartz, SiO2. All right? However, when we go into diorite, we notice that quartz starts to go away, and the amount of feldspar and ferromagnesium minerals, the black and white minerals that are so common in these rock systems, are about 50-50. And so I usually describe these as salt and pepper color. And then when we get finally into the gabbro and the basalts, the ferromagnesium minerals, which are generally black in color, and there's really the only feldspar that remains is a feldspar called the calcium feldspar anorthite. And it's kind of a grayish color. So in other words, all these rocks usually come up a fairly black color. Okay, so they wind up having these obvious predictors, right, in terms of their color. The main difference between a gabbro and a basalt is the grain size. A basalt forms on the surface of the earth, but a gabbro forms in a blister that never makes it to the surface. So the crystals are larger. Same thing with a granite and a rhyolite. Exactly the same chemistry, but a rhyolite is extruded out to the surface in a volcanic eruption, whereas a granite stays in the heart of the earth at some depth. Here's a similar chart. This one's a little more sophisticated, and it's out of a textbook that I like to use. So I had access to the image, and so I decided to incorporate it here in this lecture. And so we can see the compositions are actually labeled granitic, andesitic, basaltic, and then ultramafic. And the way you read this chart is just like the other one. We have these coarse-grained granites, coarse-grained rhyolites, and you can look at the mineral assemblage you would expect to find in a typical granite. So in this case, it's a little more sophisticated. There's quartz, muscovite, potassium feldspar dominates, sodium-rich feldspar, which is albite, biotite, and amphibole are all to be expected in a granite, right? You might be missing one, maybe you don't have the biotite or you don't have the muscovite or something might be missing from here, but you at least get the quartz and the feldspars pretty regularly. And as you go across, you realize pretty rapidly that the quartz disappears into the andesites, and by the time you get into basalt, there's no quartz. You cannot find quartz in basalt. All right, over here again, that calcium-rich feldspar. So you can remember now that this was the Plagioclase solid solution series, which is why I brought it up during the mineralogy lectures. All right, here's our dark-colored minerals, our pyroxenes, our amphibole, and of course biotite, which is that beautiful black. It almost looks like a microchip. I really like that color mineral. And then of course olivine, which is where the mineral or the gemstone peridot comes from. So even though it's intuitive to you at this point, that rocks, igneous rocks that are formed of these minerals, as we go from this side to this side, go up in silicon dioxide. We get more SiO2. So it's SiO2 rich on this side. It's not so SiO2 rich on this side. We also get more potassium and sodium. That makes sense because here's potassium feldspar and sodium-rich feldspar, right? And as you get more sodium and potassium over here, you're going to get those minerals. You don't necessarily get them over here. But if you go to the other direction, you get more iron, magnesium, and calcium. These are the ferromagnesian silicates, the mafic minerals. And so we would call these rocks over here mafic. In fact, basaltic rocks are frequently referred to as mafic or ultramafic. Okay? And of course, the temperature. This is really important to keep in mind. So this temperature bar down here at the bottom, 650 degrees Celsius, melting point for rocks of this composition, which is large amount of quartz, large amount of potassium feldspar, but not a whole lot of mafic minerals. Melts at about 650 degrees Celsius. That's the temperature at which it starts to melt, right? It doesn't completely melt away, but it starts to melt at that temperature. However, if you were to take the same thing in the form of a ultramafic peridotite, something out of a mantle, for example, it's got to be at about 1250 degrees Celsius. That's a lot hotter than what you need for a granite. So this temperature difference has a major effect on the composition of igneous rocks as we go forward. So as I stated earlier, the silica content can vary widely amongst the different kinds of rocks, right? We were talking about 45%, even 40% in certain ultramafic rocks, and more than 70% in felsic rocks. Here we see a geologist who's looking at a set of quartz veins, and these are basically pure quartz. They're white, and they're actually emplaced in a type of rock. It's a granite, and the granite is 70% SiO2. But the difference between the two, that 30% being mafic minerals and feldspars and things like that, is enough to make them very obvious, very different from one another. Okay, so these would be two, and they're both igneous. This was a liquid when it was put into place, and this was actually also a liquid when it formed. But you would surmise over time, and we'll teach you how to do this, that this quartz liquid would have come in later than this one here. So composition, it turns out, has a major effect on the behavior of magma on planet Earth. So, for example, granitic magmas have high silica content. And it turns out that high silica makes it a very sticky magma, which means it has high viscosity. It's slow flowing. Liquid exists at temperatures as low as 700 degrees Celsius. So remember, we were saying about 650 is when you start to get melting, but you really get definitive liquid at 700 degrees Celsius. And quite frankly, 700 degrees Celsius is not that difficult for the Earth to produce. It's actually fairly easy. By contrast, so the granitic magma is the really light stuff, the one with a lot of quartz and a lot of silica, all the way on the one side of the chart, on the left side of that former chart. If you're confused about what I'm referring to, just review the video a few minutes ago and you'll find it. The gabbroic magmas have much lower silica content. And remember, silica is really sticky, but if you don't have a whole lot of it, it makes it so that it's not a real sticky lava. So it has a low viscosity. Low viscosity means that it's going to be fluid-like. It's going to be really liquidy. And it crystallizes at higher temperatures. So what does that mean it looks like in nature? Well, so this is probably what we think of when we imagine lava moving across a landscape. Here we see a road, the lava's come out across it, and we can clearly, see that you can walk right over it. Here's a bush for scale. Well, if you have it really sticky and slow flowing, the lava flows will be a lot larger. So instead of, because it's very hard to find granitic lava flows, it turns out, andesite flows, which are the intermediate between the two, between the basalt and the rhyolites, have been observed. And here's one coming off of a volcano. Here's the basically the top of the volcano. We won't go into the details of the anatomy of the volcano just yet. Leave that for another lecture. But here's a lava flow coming down here. And you might not think that it's all that spectacular here in the image, but this thing here is probably several hundred feet tall, whereas this is probably 5 feet tall. This is a huge, very thick, slow-moving lava flow. Same thing has actually happened over here, and another one has come out over here. And they also don't flow very far, whereas this lava here in Hawaii can flow for miles and miles and miles. Notice this lava flow, even though it's tall, it's big, it doesn't go really even down into the furthest part of the canyon. So to kind of give you a sense of scale, you can barely see it, but there's a road right here. And so if that's a road, you can imagine that this lava flow, which you could see the kind of the ripples of the lava after it cooled, is probably, like I said, several hundred feet tall. So let's take a minute and kind of review what we've been talking about and explain why these features exist and why they behave the way that they do. So first off, the texture is used to describe the overall appearance of a rock based on the size, shape, and arrangement of interlocking minerals. Okay, we've been talking about that. Factors affecting crystal size. This is where I want you to really pay attention. 1, the rate of cooling. Okay, a slow rate promotes the growth of fewer but larger crystals. All right, this is what's really important about this. If it's a slow rate of cooling, you're going to get larger crystals. Fast rate forms many small crystals. And of course, very fast rate forms glass. So if you can actually make a magma cool so rapidly that it can't even form crystals. Another important factor is the amount of silica that's present, right? If you have a lot of silicon dioxide, it's going to actually determine the mineralogy itself. And then, of course, the amount of dissolved gases will also determine not only the mineralogy, but the ability of forming different crystals. So that results in kind of 3 important vocabulary words that we need to keep in mind as we go forward. One we've already discussed, right? Glass. So we get an igneous texture of glass, which is no crystals. But the next one, you notice I've got it in bold here. These are the aphanitic texture, which is fine grained, very fine grained. As a matter of fact, it's so fine grained you can't see it. The word aphanitic comes from aphaneru. It's a Greek word, and it means not visible. And it's basically microscopic crystals. The crystals are there, but you can't see them. And it forms from a rapid rate of cooling of lava or magma. In other words, it cools so fast that the minerals cannot grow large enough for your physical eyes to actually see them. In contrast with that are the phaneritic, or the coarse-grained rocks, or the coarse-grained texture. And this is usually formed from slow cooling, and the crystals can be identified without a microscope. You can hold up a piece of granite, and many people with a kind of trained eye can identify the quartz and the K-spar and the albite and the anorthite and whatever else might be in there. Hornblende is pretty typical too. Pretty rapidly, because these are common rock-forming minerals, and they grow big enough where you can actually see them. So here are some of those textures demonstrated. Now this is no crystals, it's a glass. All right. What's really fascinating about these four pictures, I'll come to it here in a moment. But there's a kind of a dark glass. Notice that like quartz, when it breaks, it forms a conchoidal fracture here. Here's another rock, microscopic crystals. You can't see anything, right? It just looks like a big dirty mass. It has these little holes in here. We'll be describing what these little holes are. They're called vesicles. We'll be describing them a little bit later. Down here we have some fine-grained. If you look really carefully, you can actually start to see little tiny crystals. So by definition, we can see them. It's phaneritic. It can be fine-grained phaneritic, but it's definitely phaneritic, whereas this microscopic crystals is aphanitic. And of course, the coarse-grained phaneritic here, again, K-spar, quartz, little bit of biotite is in here, not a whole lot, just a small amount. And then, of course, some albite. There's these little white splotches in here. And that's coarse-grained phaneritic. So one of the interesting things about these is, even though these rocks look completely different, they all have exactly the same mineralogy. If I take this and dissolve it in acid, take this and dissolve it in acid, take this and dissolve it in acid, and take this and dissolve it in acid, all four of them have the same chemistry. The only difference between these rocks is the size of the crystals, right? In fact, this one doesn't even have crystals, so I can't actually, by definition, call that a rock, because a rock is a definition of two or more minerals. I have no minerals because I have no crystals in here. But here I have microscopic crystals, and then here I have visible crystals, all with the same composition. So it turns out crystal size has a major effect on what it looks like in the field. Another really cool texture that comes up from igneous rocks are porphyritic textures, okay? So porphyritic textures form from, these are minerals that form at different temperatures as well as differing rates. Large crystals called phenocrysts are embedded in a matrix of smaller crystals called the ground mass. So in this image here, we can see that there are large crystals of, in this case, it's going to be potassium feldspar, K-spar. And then we have albite, not a whole lot of, I don't believe there's a whole lot of quartz in here. I guess there's some, but this is a K-spar porphyry in granite. So here we see the granite, the albite, and probably quartz would presumably be in here, some hornblende, and then these giant K-spar crystals in here. Well, that tells us something about what started forming first in this, or what was existing in this magma chamber when the crystallization was occurring. It means we had nice, happy, healthy K-spar crystals that were forming, and the other stuff started forming much later, or at least came into the existence of the magma chamber much later. So let's look at our definitions over here. The ground mass is the small grain stuff here. This is taken from a rock here. And then the phenocryst is this bigger one right here. This here is the K-spar phenocryst, and the ground mass, which is quartz and albite and mafic minerals. Okay, and two other really interesting textures to just kind of keep in mind. There's the pyroclastic texture. So various fragments ejected during a violent volcanic eruption. Typical of this would be a pyroclastic scoria. Pyro meaning fire broken. Fire broken scoria. This is a basalt. We usually just call it a scoria or a cinder. This is another word that we use to describe this. You notice it has a lot of holes in it. That's a lot of gas in there. Textures often appear more similar to sedimentary rocks. That's not atypical. You can actually go to a cinder cone and you will see layers that will look like sedimentary rock layers. Frequently contain holes called vesicles that formed from gas bubbles during the eruption. So yeah, you can see this is clearly coming out of a volcano, and it had a lot of gas in it at one time. Okay, we contrast that with its kind of intrusive cousin. So this is the one that extrudes very fast, the gases get out. What if it cools very slow and the gases never get out? Well, that gives us this thing down here. So this is a pegmatitic texture. It's exceptionally coarse grained, really large crystals actually, that form in late stages of crystallization of granitic magmas. So here we see pegmatite crystals of elbaite and muscovite, and these are large crystals. They're actually, unfortunately I don't have the scale on here, but they're several inches long. Down here is another purple mineral, and I believe these are called lepidolites, and I believe these are collected from a magma chamber, a pluton in the San Diego County area. All right, so we've kind of gone over these things. Let's kind of go through the suite of rocks. You know, we kind of have been throwing out what granites are and rhyolites are, but let's actually look at these things. So let's look at the granitic compositions first. So to do that, of course, you're going to start with the granite. And so here we see the composition. You can see the individual crystals all over the place, right? Here's some mafic mineral, probably hornblende. White mineral in here is going to be the mineral albite, pretty typically albite. It's a feldspar. The pink stuff is potassium feldspar. We call it K-spar. So usually when you see pink or orangish pink, it's usually potassium feldspar. And quartz, which is actually about probably 15 to 20% of this rock, is a little harder to see. Because the grains are usually small, but they're these gray ones right here. They're not black. This is a black one here. But right next to it is a quartz grain. That's that gray stuff right there. There's another gray one there. That's another gray one over there. And that's all quartz. So a couple things to notice about quartz. One, you'll hear it brought up over and over and over again that it's a major component in the continental crust. And as a matter of fact, we use granite as the model for the continental crust. Sandstones are usually made out of quartz that are taken away from granites, and beaches are made out of material that's eroded from granites, and so on and so forth. So it's usually the parent rock that almost everything else is assumed to be derived from. Things get a little more complicated in detail, but in general, that's the assumption. All right, notice also the color. That's this white, orange, speckled black rock. Okay, so it's a light colored rock. It also has a density of 2.7 grams per centimeter cubed, so it's 2.7 times heavier than water. Okay, now let's go to its, and notice that also because it's got visible structure or visible crystals, we would call this a phaneritic rock. Phaneritic meaning visible crystals. Here is a rock called a rhyolite that has exactly the same chemistry. Let's go back to the granite. This rock and this rock have exactly the same chemistry. They even have the same minerals in them. Look how pink it is, right? All that pink is none other than the same pink that's in here. But it's so small that it dominates the color of the rhyolite. So the rhyolite, it turns out, is the extrusive version of granite. It's the part that comes up to the surface. It's the lava. And rhyolites are very, very explosive. They're very viscous. They have a lot of silica. And things that are really viscous and really silica rich create large explosions. Notice that it's very hard to see if there are any other crystals in here. Occasionally you might see a little piece of debris in here, probably, you know, here and here and here. That probably is what material that was taken up into the rock during the time of the eruption, because it blows up other things around it and it winds up in the rock mixed with it. But aside from that, we don't really see anything else. This is a really beautiful rhyolite. Okay. In contrast with the rhyolite, we have something that is not even got any minerals, no crystals at all in it. It's got the same chemistry. It's probably got the exact same stuff in it that would make quartz and K-spar and albite and all these other things we've been talking about. But it also has a little bit of mafic minerals in it as well. But notice this conchoidal fracture. Notice that we don't see any crystals anywhere. This is a glass, right? This is a granitic material that never formed any crystals because it got cooled so rapidly that crystals didn't have time to form. And so the type of rock that this is called is obsidian. Right? And we usually refer to all forms of volcanic glass because essentially this is a volcanic rock. This cannot form underground. It can only form up on the surface. It can be a little challenging from time to time to figure out whether or not it's granitic or whether it's basaltic or whatever because it's all glass no matter where you look. You have to do some chemistry to figure that out. But nonetheless, it's kind of cool to think that this rock, and that rock have exactly the same chemistry. They just have different crystal sizes, or as I like to say, no crystals in obsidian at all. And the last one of this group I want to talk about is something called pumice. And pumice is a form of scoria that is ejected out during a rhyolite explosion, during a volcanic explosion where the magma chamber is made out of granite. The rhyolite is erupted out. And as it erupts out, the holes expand that have all the gas in it. And you can actually get so many holes in it that it makes the rock lighter than water. And so we could see here's a rock that's actually floating in water. Pumice is typically used in cosmetics for exfoliating the skin, things like this. But they form very, very violently. So next time you're exfoliating with some pumice rock or pumice stone or whatever, just know that it came from a very violent eruption that probably did tremendous damage to the environment when it went off. But you might be saying, so it has these holes in it. I don't see any crystals in here. Yeah, it turns out that this is exactly the same thing as this. It's obsidian, except it's obsidian that had a lot of gas in it. And so that gas, as it expanded, it blew holes like this all over the pumice rock or the pumice stone. And that's what you're seeing now. And if we were to look at it through a microscope, you wouldn't see any minerals at all because the gas expanding and getting out actually cools the rock so fast that it doesn't have the chance to form minerals. This is really, really cool rock. There's a lot of open pore space in here that makes it light. All right, so we talked about the granitic rocks. So let's talk about the intermediate rocks. We're headed towards the all-black basalt, which are very famous, and everybody knows what a basalt looks like. But andesites are a little strange for some people to think about. It's kind of a half basalt and a half granite. And so the diorites have a combination of the two. So as a consequence, we refer to them as intermediate rocks. And the principal type of andesitic rock is called a diorite. And this is the Plutonic equivalent of andesite. Now, andesite gets its name from the Andes Mountains. The Andes Mountains are made largely out of andesite. It's coarse-grained, which means it's plutonic. That makes sense, right? Or I'm sorry, it means that it's phaneritic. And that makes sense, right? Plutonic rocks generally make phaneritic, coarse-grained materials. It's intrusive, which is implied by the fact that it's plutonic. And it's composed mainly of intermediate feldspar and amphibole. Intermediate feldspar means it's partly albite, partly anorthite, which is to say partly sodium, partly calcium feldspar. And of course, it's going to have lots of amphibole, like hornblende in it. So here we see an andesite porphyry. So here we see the andesite. This is an extrusive version of it. Notice it's got a nice salt and pepper texture to it. But inside of this andesite, back in here, it's kind of hard to see the crystals. If you look really hard, you might be able to see little fragments of things. But then you have these larger fragments in here. So that makes it a porphyry. Okay, but it's still an andesite. Here's the diorite. The diorite is the intrusive version of it. Let's go back to this. This is the extrusive. So this is actually from an eruption, and it had crystals already in it when it started to erupt. This is where it never actually erupted, or at least not that we know of. This is the heart of the magma chamber. This is the heart of the volcano, or the heart of the Pluton. And you'll notice that there's basically two kind of minerals in here. There's something mafic, and there's something that's intermediate felsic, right? Intermediate feldspar. between these two. And I call this a salt and pepper color, or salt and pepper texture. You can definitely see all the little crystals, definitely something here. It's probably hornblende. And then, of course, the intermediate feldspars throughout. There is no quartz in this rock. That is an important thing to take note of. This is a diorite. So that leads us to basalt. We've gone over granitic compositions. We've gone over andesitic compositions. Now we need to get into gabbroic compositions, of which basalt is the extrusive version of gabbro. So here we see a basalt. This one actually has a lot of iron in it. You can tell because there's a fracture right here. And that fracture had some water in it, and that water rusted the iron in the rock, in the ferromagnesian silicates. And so it has that orangish ring to it. You see that same orangish ring down here and up in here. Wherever there's a fracture, a fresh fracture, you're going to start seeing some rusting of the rock. It's the irons, the ferromagnesian silicates in the rock that are rusting. All right, so this is a basalt, nice black rock. Notice that there's little tiny holes here, little vesicles here, but for the most part, you don't see any crystals, right? You might convince yourself you're seeing something in here, but it's really just surface discolorations from weathering. However, here's a gabbro. These two rocks, the basalt and the gabbro, are chemically identical to one another. The difference between these two rocks is the grain size. So here we see nice large crystal here, nice large crystal here, and even some other visible crystals all throughout. Here's some nice hornblendes, or actually these are probably pyroxenes. I take that back. These are probably pyroxenes. And there's almost certainly some calcium feldspar in here, also called anorthite. Those same minerals are also present in here in the basalt. You just simply can't see them. All right, so I hope I didn't put you to sleep going through this lecture. And as a matter of fact, I'm hoping that you come out of this and you're excited about igneous rocks. We're going to be heading into some really cool stuff in the next couple of lectures. We're going to get into volcanoes and where volcanoes come from and what causes their behavior. And of course, these igneous rocks are in fact the key to understanding what volcanoes do. Anybody who's a volcanologist really knows their igneous rocks inside and out. So hopefully I can turn your feeling of wanting to lay down your book. Hopefully you're not waking up and the video is just over. Hopefully you're actually looking more like this, right? So we hope to see you in the next lecture real soon. If you have any questions, as always, send me an email. Until next time, bye.